Hello friends and welcome to the second lecture of module 4, that is analysis of gradually varied flow profiles. The learning objectives I will understand how to derive the flow profile taxonomy, provide nomenclature to various profiles, will examine the GVF profiles for different conditions, and using all this knowledge we will synthesize it to derive the GVF profiles if a composite profile is provided to us. So let us start the first part where we assign a taxonomy to given flow condition. So the taxonomy is a way to assign the nomenclature to a particular flow profile depending upon its flow condition. So the usual format is there is a letter which is followed by a number. So it can be x1, y1, z1 and so on. So there is a letter and it is a number. It could be x2, z2 and so on. So what does that define? So the leading letter, that is x, that means the type of reach or type of slope based on the normal or critical depth. So in the previous lectures we have already studied that based on the comparison of normal and critical depth we have different types of slopes. So if your normal depth is greater than the critical depth you have a mild slope, so it is denoted by m. So this x is this letter, so if it is mild slope it is m. If yn is less than yc it is a steep slope, so it is s. And if yn is equal to yc it is a critical slope, so it is c. Now these three slopes are called sustaining slopes because the slope is always positive in the direction of flow. So the channel slope which it falls in the direction of flow. So your sustaining slope is always positive. So it is also called a positive slope. Now there are special cases, the one where we have a horizontal slope, so S naught is 0, so your Yn is infinity. So that is horizontal slope H, and adverse slope where Yn is negative, so that is an adverse slope. So these two slopes are called non-sustaining slopes because they rise in the direction of flow. So they are zero in the direction of flow, or they rise in the direction of flow. That is why they are called non-sustaining or negative slopes. So usually the horizontal and adverse reaches uh, would not generally occur in both man-made structures or in the natural environment, so it depends. However, practically if they occur they will be of very short length, because if you know adverse slope of very long length, then it will no longer be an open channel flow, it will not be a gravity flow, so that is why. However, owing to lack of gravity to support the flow of water, such reaches can exist over relatively shorter distances. Now, so we understood the first letter. Now we understood from where the number comes, that is a subscript. So the subscript number is based on the comparative relationship between the actual depth of flow, which is y, and with normal and critical depth. So it is classified into three zones, that is zone 1, zone 2 and zone 3. So the subscript number can either of these three, it is 1, 2 and 3. So 5 types of slope and 3 types of numbers. So we may have some 15 combinations maximum which are possible, out of which are feasible, that we will see. So if your depth y, that is greater than yn and yc, so that is zone 1, irrespective of your slope whether it is a mild or steep slope, if y is greater than yn and yc it falls in zone 1. So here if this is a mild reach, so it is m and zone 1, so it will be m1. Similarly it is a steep reach and zone 1, so it is s1. Now if yn or yc is greater than y and is greater than yc or yn, so it may fall, it is a sandwich position, it will fall somewhere in zone 2, so it can be m2 or it can be s2. So it can be either of those. Now The third part where your yn and yc both are greater than y, so in that case it can be in zone 3, so it can be either m3 or in this case it can be s3. So these are the nomenclatures. So based on that, first you classify which is a type of slope and classify the type of zone, and then you can name the particular GVF profile. Okay, so it is very simple, and we'll move forward. Now there are some special features to this GVF profile, so we'll understand that and then we'll analyze it. So first is, we may encounter discontinuities in the flow profile. So what happens when your y is equal to yc, your GVF equation would yield infinity. We have derived different forms of GVF equation. So in one GVF equation, your yc comes in the denominator. So if y becomes yc, then dy by dx will become infinity. So when so the change in slope is infinity. So that is tan theta is equal to infinity is possible where, when your theta is equal to 90 degree, at that point only your dy by dx will be infinity, and this implies that the flow profile will be vertical in the line in crossing the critical depth line. So your flow profile will be vertical when it is crossing the critical depth line. Now usually we see that there is a sudden change from low to high stage. So in that case, if we observe the specific energy curve, so from low stage it is supercritical, high stage is subcritical, so it has to cross this stage. So it will cross the critical depth line and a hydraulic jump will occur, and that would be represented as a discontinuity in the flow profile. So flow profile is not continuous at that point. So if the depth changes from high to low stage, so it's opposite. So from high to low stage, then it is called a hydraulic drop. So at or near the critical depth line, the flow profile is bent to produce great curvature, so that the assumption of parallel flow, which is used in deriving the GVF equation, is no longer valid, and it would induce large errors because flow at that point would be curvilinear or rapidly varying. So this is one special characteristic where you need to consider when y is equal to yc. Now, next is behavior of flow profiles at some specific depth. When y is infinity, your dy by dx is s naught. That means flow surface is horizontal. So that is again known to you. When y is equal to yn, your dy by dx is 0. That implies your flow surface is parallel to channel bottom and it is a uniform flow. And when y is equal to yc, a hydraulic jump or drop in the flow profile may occur. And lastly, when y is equal to yn is equal to yc, the flow is uniform and critical. So this behavior occurs at different depths. Now, since it is a curve, so it encounters a point of inflection. So point of inflection is one where, let us say this is a point of inflection. So on either sides it has different slopes, so it changes its slope on either side. So when y is equal to 0 in the GVF equation, it produces an indeterminate form, so it will have infinity by infinity. So it becomes apparent that there should be a point of inflection on the flow profile. So there are two ways. So when it is transiting from y less than y into yc, so there will be some change in the curve. So this is one point of inflection, and so it is very close to the channel bottom because here it will be almost vertical. And second, when your y is greater than yn, so this is in zone 3 and next is in zone 1. So at these two zones there will be point of inflection, and this will be very close. It will not touch the horizontal level, but it will be very almost an asymptote to the horizontal level. So these are 2 point of inflections which are possible. Now let us classify the flow profiles. So as we saw that there could be 15 combinations possible, but in reality only 13 combinations are possible. The two are not possible, that we will see which two are not possible. So there are 13 GVF flow profiles which are possible. The flow profiles which are possible, out of which 12 are GVF and one is for uniform flow. There is one condition which yields uniform flow only. Okay, so let us see your first one, that is M profile, which is on the mild slope. So the characteristics are, so there are three profiles possible: M1, M2 and M3. So in M1, here Y0 is to be read as Y, synonymous to Yn, that is the normal depth. So I've made that changes. I've made it to Yn so that there is no more confusion. Okay, so your M1 profile would exist when your Yc is less than Yn less than Y. Okay, so your when your Y is greater than Y and Yc, so M1 is a backwater curve where your dy by dx is positive, and it is a subcritical range where your Froude number is less than 1. So it is this type of curve where it increases in the depth. So this is the example of M1 curve you can see. M2 curve where your Y is in zone 2, that is it will between Yc and Yn. So always remember, for mild slope your Yn will be greater than Yc. So it is in zone 2, so it is a drawdown profile because your dy by dx is negative and it is a subcritical flow. So we can see this is a drawdown profile. Now M3, where your Y is less than both Yc and Yn, so it is a backwater profile whereby dy by dx is positive, but it occurs under supercritical flow condition. So you can see this is a supercritical flow, and here your M3 occurs. So somewhere here there will be a hydraulic jump formation. So more clearly we can see here. So in any figure, when we plot the flow profile, we'll represent the CDL, that is a critical depth line, and we'll represent the NDL. So in case of mild slope, your NDL would always be greater than CDL. So this is your M1 profile, so it will be horizontal asymptote here. This is M2 profile. Now why it is shown with a dashed line? Because it does not touch here, so it is vertically meeting here, so there is a discontinuity in the flow profile, so it is shown by a dashed line, so it is almost vertical when it touches the CDL. And similarly your M3 profile also, so these three profiles can be shown. So this is zone 1, zone 2 and zone 3. So let us understand where practically you can find these profiles. So the first profile, that is M1. So this is formed behind a dam in a natural river. So in a river you construct a dam, so you create an obstruction. So now remember, when we are dealing with mild slopes, your NDL will always be higher than the CDL. So that is plotted. So these are just hypothetical situations where we are plotting it without any actual data. If you have actual data, which you will see in the next lecture, we can compute it and plot all these profiles. So you have this M1 profile because there is a backwater curve being formed, and that is your dy by dx is positive and it is in a subcritical zone upstream of the dam. So M1 profile is formed. It is also formed when a canal of mild slope is joining two reservoirs. So reservoirs have a high pool of water. So in the mild slope, when it is joining the two reservoirs, so this again a backwater curve and M1 profile is plotted. So this way you can plot the profile. Now M2 profile is a drawdown profile. So your dy by dx is negative. So it will be falling in the zone 2. So this profile is formed upstream of sudden enlargement of the canal. So this is a canal which is going on, and after a particular section, the canal is widened. So in that case, on the upstream of the canal, you can see the water level will fall down. So due to that, your mild slope So due to sudden enlargement, the M2 there will be a drawdown curve because your width would increase, so your normal depth would fall a bit as compared to the upstream, and there will be a drawdown curve and your M2 profile will be formed. So remember, your flow will always adhere to this normal depth. So it is very essential to locate your NDL and CDL, because CDL will give you whether there is it is passing through a critical depth line or not, or it is remaining above or below it. So this is M2 profile. Another can be when there is a canal which is leading to a reservoir where the water pool is always there. So there are two cases possible where the pool of water is above the CDL or below the CDL. In both the cases, it is less than the NDL, and then it would fall and meet those water pools in the reservoir, and again it would yield an M2 profile. So it is a drawdown profile again in the subcritical zone. Now the M3 profile that is formed just below the sluice gate. So this is a sluice gate, so there is water being ponded upstream of the sluice gate, and we just raise the sluice gate, so water would rush out, and then it will be having a backwater curve. Then a hydraulic jump will be formed because it has to overcome this critical depth line, and then it would join the normal depth line. So that way your flow profile can be traced, and this is your M3 profile, and this is accompanied by hydraulic jump because it is a transition from supercritical to subcritical flow. Another case where M3 profile is formed, where there is change in the bottom slope from steep to mild slope. So this is a steep slope channel, and at a section after that it becomes a mild slope channel. So in steep slope channel, your CDL would be above NDL, and in mild slope channel, your NDL would be above the CDL. So just as I told, joining the NDL line, so your NDL line is here, one NDL line is here. How to join them? This is a supercritical flow. So to overcome that, it would have a hydraulic jump. So this particular profile which forms on the mild slope, that is an M3 profile, and after that a hydraulic jump takes place and it would join the NDL. So you get a M3 profile. Okay, so let us move to the S profile now. So similar to the mild slope, we have three S profiles, that is S1, S2 and S3. So in S1 profile, your y is greater than yc and yc is greater than yn. So in S profile, always your yc would be greater than yn. So this is in zone 1. So it is a backwater profile with a subcritical flow. So you can see this is a backwater profile with a subcritical flow. S2 profile, that is in zone 2. So it is a drawdown profile and it is in supercritical flow. So we can see this is a drawdown profile. So what we saw, that so far the zone 2 profiles have been of the drawdown type. S3 is a backwater profile because Yn is less than both Y and Yc, and the flow is supercritical. So here we can see that it is an S3 curve. So in this case, we can see that this is a critical depth line, so it is shown by dashed line because there is discontinuity in the flow profile, and it shows a horizontal asymptote. Similarly, this is a drawdown profile, that is S2, and S3 is again a backwater profile. So let us practically understand where this profile is formed. So similar to M1 profile, your S1 profile is formed behind a dam in case of a steep channel. So in case of a steep channel, your CDL is greater than your NDL. So in order to have a transition from supercritical flow here to subcritical flow, a hydraulic jump would be formed, and then your water surface would rise, and thus a backwater S1 profile is formed. Similarly, the next S1 profile can also form when a steep canal empties into a pool of high elevation. So you have already a pool downstream of high elevation, So this is a steep canal and it has to meet this high water level pool. So a hydraulic jump would be formed and followed by a S1 profile, again of backwater nature, to meet that pool. Now S2 profile, it is a drawdown profile, zone 2. So it is formed in the downstream side of a channel enlargement. So your channel is enlarging. So here it will be formed on the downstream side of the enlargement, and there it is a drawdown in nature. So it dy by dx is negative and it is an S2 profile. Again, S2 profile can be seen when there is a transition from steep to steeper. So steep and steeper means it becomes more steep. So that is the relative degree. So if it is less steeper, then it can be on the lower side. So it will be still steep, but lesser degree of steep. So the CDL is always greater than NDL, but in case of steep profile, your NDL is higher, while in case of steeper, your NDL becomes lower because it has gained much steepness. So again, you can see that it is a drawdown profile. The water will flow along the NDL. It will be joining two NDLs and it forms a S2 profile. The next one is S3 profile. This is a backwater profile, but it forms under supercritical flow condition. So first case, the profile on steep slope side as slope changes from steep to milder steep. So this is steep and milder steep matlab it becomes little bit less steeper. So your NDL was less here. Now NDL has become little bit higher, but still lesser than the CDL in both the cases. So to achieve, now if it would have been above the CDL, then a hydraulic jump would have come. But since it is below the CDL, so there is no jump. So it is simple, a backwater curve and S3 profile is formed. Last is below sluice gate with the depth of entering flow is less than the normal depth. So if the depth of entering flow is greater than normal depth, then this profile won't be formed. So the depth is very small here and it is less than the NDL. So it will go and join the NDL and S3 profile will be formed. So this is all about the S profile. Now we move on to the C profile. Now in C profile, there are three profiles possible. So C1, where your YC is equal to YN and Y is greater. So it is in zone 1. So it is a backwater profile and it is in the subcritical zone. Now C2 is a special case where your Y is equal to YC equal to YN. So that means all the three are equal and that is only possible in case of a uniform flow. So we discussed out of the 13 profile, 12 are GVF and one is a uniform flow profile. So C2 is a uniform flow profile. Okay, and the last is C3 where your Y is in zone 3. So it is a backwater profile and it is supercritical in nature. So you can see the C zone profiles are both backwater profiles. Now this C zone profiles, so when they are meeting this CDL, now here this NDL is equal to CDL, both are same. So don't get confused in C profile, your NDL is equal to CDL. So you may argue that this C3 profile, it should meet vertically to this, but in that case it is NDL, and here where it is meeting vertically, it is CDL. Now the C1 and C3 profiles are very rare and highly unstable. So usually they are used to represent a transition between M and S profiles and vice versa. So that is why the C profiles are used. Next is the H profile. So H profile, you have only two profiles possible, H2 and H3. H1 is not possible because the normal depth is infinite and thus this profile cannot exist. So your normal depth is infinite in case of a horizontal channel. So H2 profile, since it is in zone 2, it is a drawdown profile. So your YC is less than Y. So you can see H2 is a drawdown profile, and H3, your Y is less than YC, and it is a backwater profile but on a supercritical flow. So it is a backwater profile. It is similar to your M3 profile. So the horizontal slope profiles are just an extension of mild slopes, such that your slopes are tending to zero. So where we can see so here you can see that when they meet the CDL, so there is a discontinuity which is represented by a dashed line. So in practical example, where we can see H2 and H3, that is when the flow is happening below sluice gate on a horizontal bed and it is followed by a drop. So this is a sluice gate. So this flow is going from sluice gate. Now remember, on a horizontal bed your Yn would be infinity. So this is a very high, infinite depth of pool of water is there. So the when flow comes below the sluice gate, it is a supercritical flow, and to join this pool a hydraulic jump has to be formed to cross the CDL. So this is an H3 profile. And further, where there is a drop, so at the brink of the dot, so this is a brink, so this is a brink where critical flow condition will be there, and then it will be falling down. So this is a drawdown profile of zone 2, so it is an H2 profile. And the last is your A profile, that is a adverse slope. Again, since your normal depth is infinite, your A1 profile is not possible. So out of 15, H1 and A1 are not possible. C2 represents uniform flow. So remaining 12 are your GVF profiles. So in zone 2, your YC is less than Y. So that is a drawdown profile and subcritical in nature. So this is the zone 2 profile. And in zone 3, Y is less than YC, so it is a backwater profile of supercritical nature. Now, these profiles are of very short length, if at all they exist in nature, because they are non-sustaining slopes. So one thing we can see clearly, that the zone 2 profiles are all drawdown profiles. So in all 4 drawdown profiles are there: M2, S2, H2 and A2, and remaining 8 are backwater profiles. So if you are given a composite profile, then you should be able to sketch the resulting profile. So let us see, there is a mild slope followed by a steep slope followed by again mild slope. So what kind of resulting profiles can be there? So the very first thing that you need to do is to sketch your NDL. So this is a mild slope, this is a steep slope, and again followed by a mild slope. So let us sketch. So first what I practice is, I'll sketch the CDL, because CDL remains constant, it does not change with the channel slope. So this is my CDL. This will be the control section here, and this is your CDL, another control section. So I'm sketching it very roughly. So this is your CDL. This, since it is a mild slope, your NDL would be greater than the CDL. So this is your NDL. Steep slope, your NDL is less than the CDL. And again mild slope, your NDL is greater than the CDL. So let us draw the flow profile. So water would follow the NDL path. So here you can see there would be a drawdown, so it will meet the CDL. So I will make a dashed line and it will meet here. So this is a drop. So M2, here again a drop, so it will be S2. Now to cross here, there are two cases possible. One case, there will be a hydraulic jump here, and it will join here with the help of a S1 profile, or another case will be it would extend further here and a jump will be formed on the mild slope and it will join the NDL. So this would be your M3 profile. So this is also possible. And if we modify the condition such that here there is a hydraulic, there is a drop, so it may follow here and it may, sorry, it may drop, and again you will have M2 profile. So why, now you may wonder why there are two profiles forming here, that is S1 and M3. So they will depend upon this NDL. So we have studied conjugate depths. So for a hydraulic jump to form, this depth should be conjugate to this depth, then only the jump will form. So if not, then it is moved ahead such that these and these depths are conjugate to each other. So let us say if this is y1 and y2, if at all they are conjugate, then jump will form here. If not, then there is a new depth y1 dash which is conjugate to y2, then jump will form at this end. So it depends upon the availability of conjugate depth. So like this we have synthesized all the GVF concepts and we can plot the composite flow profiles in this particular case. So you can solve more problems and gain more insights on that. So with this we end our today's lecture. In the next lecture we'll discuss how to compute the length of this profile. So this length of profile, how would we would compute that, and that we will see in the next lecture. So thank you very much and have a nice day.